Okay, let's have a quick overview of the air conditioning system. So we have two air conditioning packs located up in the wing center section that takes air from the bleed air supply, be it from one of the two engines or the APU. The air from that bleed air supply passes through a flow control and shut-off valve where the pressure is regulated, and then makes its way through the cooling cycle. So passing through a couple of heat exchangers, a cold air unit comprising of a compressor and a turbine, and it passes through there, and coming out of the packs, we have temperature regulated air that then gets distributed. So it first makes its way along into the distribution lines, and if we look at the cabin distribution, it passes through a distribution box which has a rotary actuator on it to divert the air out through ceiling ducts or floor outlets in the main cabin, and also passes forward to the cockpit distribution. We're going to go through the cooling pack operation in another slide. The pilot interface will be the air conditioning panel or ECS panel, and here we've got some switches for the recirculation fan, the EFIS fan and the avionics fans. We've got the cabin control mode selector, which is either auto or manual, normally would be in auto. We've got the cabin and cockpit temperature selectors to control either in auto, the temperature in auto or manual modes. Then beneath the rotary temperature switches, we've got the main pack switches which control the two flow control valves. We've got a cross bleed valve switch, normally would be closed, is shown in this picture as being open. And that allows one source of bleed, one single bleed source to supply both air conditioning packs. And then on the bottom row, we've got the main bleed control, either on or off, for the left-right engines and the APU. We've also got a flow mode controller in the center, and we can select either normal or high flow mode. And that controls the flow output from each of the air conditioning flow control valves. The recirculation fan the actual fan has two speeds, high and low, or of course off, and when it's selected on, the speed of the recirc fans is determined by the position of the flow mode switch. So the crew don't control the speed of the recirc fans directly. When the flow mode switch is in high mode, the recirc fans speed is in slow mode, and when the flow mode is normal, the recirc fans are in high speed mode. Okay, so let's go through the operation of the air conditioning pack. So the bleed air source will come from either the engine or the APU or the other engine, as long as the cross bleed valve is open. This is showing the right-hand pack. The left-hand pack is basically identical. So the air will pass through the flow control and shut-off valve and make a pass through one of the two heat exchangers. So it passes through the primary heat exchanger first. And hot air is also tapped off along this line and becomes available to the temp control valve. The heat exchanger is cooled by ram air that passes through an inlet on the top of the center wing area, passes over the heat exchangers and cools them down, and is exhausted out through an exhaust vent on the side of the wing to fuselage fairing panel. When we're on the ground, there's an electrically operated heat exchanger fan that draws air across and blows it out as if it was ram air. So it draws air through the inlet here passes it over the heat exchanger and then out overboard. At this part of the ducting, there's a check valve, a flapper valve, which acts as a check valve, so that when the heat exchanger fan is operating, it's forcing the air in this direction rather than letting it go out through the inlet, which would probably be the easiest route that it would take otherwise. So here's a thing now. First top tip. Sometimes you might have issues where the crew complain that when the aircraft's on the ground, the cooling doesn't work very well, it's not very efficient. One of the first things to check before you start replacing components is you check that this check valve is closing properly. Very easy to check. You don't need to run the engines or have the air conditioning pack running. You can just go up with the aircraft power on. You can go up to the cockpit, switch on the air conditioning pack switch. Obviously there's no air, so the packs aren't going to be running, but by merely switching the switch, if we're on the ground below 120 knots, that will cause the heat exchanger fan to work. It will come on, it's quite noisy, so you'll definitely know if it's working. That's the first thing, to make sure that fan is working. And the other thing is to make sure that the check valve is working properly as well. So you can just put your hand in the inlet with a ground cooling fan working. There should be no or very, very little air coming out of this inlet. If you see a lot of air coming out of this inlet, then it means that the check valve is not working properly, and you can either just lubricate it or make sure it's working freely or replace it. And that could solve that simple problem of the air conditioning packs not working when we're on the ground. So the air from this hot air coming from the bleed source will pass through the first heat exchanger and hit the compressor, where it's going to compress the air and heat it up. Air is then passed along to the secondary heat exchanger, and just before it goes into the secondary heat exchanger, there's a temperature switch here that operates at 220 degrees C, and it causes the pack to shut down if the temperature is too hot and it goes above 220 degrees C. It will then pass through the secondary heat exchanger and come along to a condenser, then passes to the turbine inlet, where we make it do work and it gets cold. It will then pass through a water extractor, through the center of the water extractor, through the core of the condenser, and then pass through a check valve and into the distribution system in the cabin, where it will get distributed through the upper or the ceiling outlets or the floor outlets, and the proportion of air coming out of each of those is controlled by this distribution box, which has a rotary actuator on the end to vary the outlet proportion of air through the upper and lower ducts based on temperature. So basically we have, if it's cold air that we've selected, it's going to come out the ceiling ducts, and if it's warm air, it's going to come out the floor outlets. And the air goes through into the cockpit, where it comes out cockpit distribution ducts. And then air is also recirculated. We have 2 recirculation fans, effectively 1 per pack, controlled by that single switch, that draws air from either the cockpit or the cabin and basically recycles it into the distribution duct. And that is it in a nutshell. Oh, the other thing I didn't mention here, this low limit system. So the low limit system prevents the air in the turbine area getting too cold and potentially causing fog or ice in the distribution ducts. So there's a low limit valve here that opens up if it gets below 25 degrees C, and just allows some hot air to come in to keep it a little bit warmer and stop everything freezing up inside here. The temp control valve allows the hot air that has been uncooled to be mixed and injected into the air coming out of the turbine, which is cold air, and that's part of the temp control system to control the temperature in the duct and to achieve the target cabin or cockpit temperature that we've selected. Okay, so let's take a look at the electrical control of the flow control valve just down here. This flow control valve is energized to open, and there you can see a ground signal there. You can see the solenoid on the valve. So if we get power down this line here, the valve will be open, the flow control valve will be open. We have a power supply up here from 28 volt DC bus 1, and we've got our switch. Currently the switch is shown in the off position, and in the off position power is routed down through the switch and down through that diode and into the switch light, where it illuminates via the dimmer the off light on the switch. When we turn the switch on and command the pack to come on, that power is going to be now routed down through the closed contacts B1 and B3, passes through that diode, and through the dimmer will illuminate the white stripe bar flow tube to indicate that it's switched on. So here's the first point to point out. This when you see this switch, or when you see this indicator, this vertical bar in the switch, all it really means is the switch is switched on. It's not related to the actual position of the pack valve itself. So we turn the switch to the on position, so that means contacts A, 3 and 1 will close, and power is now going to be routed down to the first relay, which is 3HB. And as long as 3HB is de-energized, which it is here, B3 and B2 contacts will be closed, and power will come down, and boom, 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 the pack valve will open, will be energized open. So that's going to be good as long as 3HB is de-energized. 3HB is this relay here, which is the overtemp relay. This is the actual relay. That's one of the contacts, the B set of contacts for that switch. So power comes down to the overtemp relay. It's looking for a ground signal. Where can it get a ground signal from? Two things can create the ground signal. One is an overtemperature condition. This is that switch we mentioned just earlier, 210 degrees. Or an overpressure condition in the bleed air system. So in the main bleed air system. So if the temperature is hot, for example, gets to 220 degrees, the temperature switch closes, a ground signal is provided there, and that will cause the 3HB relay to energize. And once it's energized, another set of contacts in the 3HB relay, the A contacts, they will also close and provide a latch-in circuit to keep the 3HB relay held closed. And it will be held in the energized position as long as the switch remains in the on position, because once the 3HB relay energizes, B2 and B1 contacts over here will change over. That means you're going to lose your electrical supply to the valve. The valve will going to shut, and when the valve shuts, of course, we would expect the temperature to drop. And when the temperature drops, the temp switch opens and we lose the ground signal there, but because of this latch-in circuit here, it's too late. Then that relay, the 3HB relay, will remain energized until we turn it off and turn it back on again. So in other words, we have to reset the pack by turning it on and off to try and recover the pack and get it working again. All right, so what we're going to look at now is the control of the heat exchanger fan or ground cooling fan that draws air across the heat exchangers when we're on the ground. And as you can see from the statement here, when we're on the ground, if we're below 120 knots. Actually, the ground side of things doesn't, whether air or ground doesn't matter. It's the speed that's important. So we've got this picture is showing both systems, the left and right system. So we just concentrate on one system the other system is the same. So for this heat exchanger fan here, what we need to do is close this relay here, or contacts here, 58 HB, and when we do that, from the non-essential buzz, the motor will simply run. So what's going to cause this relay or contacts to close? Well, that contact there is 58 HB is here. The actual contact, the relay for it. So we've got to get power down here, boom, 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 and when we energize this, that will close that, and the fan will run. So the first thing to note is obviously the pack must be in the on position. It's pointless having the fan running if the pack's not switched on. So the switch must be in the on position, and that will put power down to here, and it comes along to the A1 set of contacts of this relay 56 HB. It also puts power to the actual 56 HB itself, and we're looking for a ground signal, and the ground signal can be provided or is provided by the air data computer if we're below 120 knots. So if we're below 120 knots, the air data computer will provide a ground signal, boom, boom, boom. That energizes 56 HB, which is here. That puts power down to 58 HB, boom, and when 58 HB comes on or is energized, these contacts will close and the ground cooling fan will operate. This part of the circuit here, I won't go through it in detail, but what I will tell you is this part of the circuit here is to allow either air data computer to provide that ground signal and turn on both packs. Both cooling fans. So both cooling fans can come on by either a signal from ADC1 or ADC2, and that's the reason for this part of the circuit here.